So you have to have a minimum, there's tests that have to be done, which you have to perform to a certain level with the strength. But you want to make it as light as possible. So what's the trick? They started, and I didn't bring them with me, but they started with steel beaners. In the 50s, 40s, 50s, every carabiner was made from steel. And it weighed like 300 grams. Then they made the carabiners from aluminum. And the aluminum had to be quite massive in order to be as strong. So they had maybe 200 or 150 gram carabiners. Progressively, they made improvements using alloying elements to create distortion, to make it more difficult for the rug to go through. The dislocation gets stopped here. In order to initiate the dislocation from moving, you have to bring more force into the system. It means you can go higher and it will still come back. You don't get to move your atoms around, so you still have the same shape. So progressively, they've improved the elastic limit. They brought it higher and higher and higher, and because of that, the beaner could be made lighter and lighter. Today, the lightest beaner, I think, 22.5 grams. Composite are sometimes a good idea to reduce weight, absolutely. And I think I have many, many examples later that I will show. No, this is not a composite. This is an aluminum alloy. So we already saw now two ways of increasing the elastic limit, which are
Alloy.
adding an alloying element, yes, and creating smaller grains, which increasing the number of grain boundaries. So here you see the grain boundaries, here you see how they are started. So at different locations you start the crystallization process. So it's like when you take water and you freeze it. Well, here you take a hot metal and you cool it so it gets frozen. But it freezes from different locations. Every location starts very nicely arranged, very crystalline, but at one point, boom, 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 it touches, and then this grain has a different orientation from this one, has yet another orientation from that one, and so on. And so you create the different crystals. And if you want to have smaller grains, what you typically do is you will do certain things to the original bath. Like, for example, you can use electricity, and you can do a pulsed electric field in the system, which will generate many, many, many locations will start, and then you have much smaller grains, for example. And I mean, I can go into more details, but I think it's just the concept. Where do we see grains? It's interesting, if you look at these galvanized poles are actually even, well, this is galvanized. So the rail here, if you look at it carefully, you will see little flakes of different gray shades. Every one of this flake is actually one grain. Fairly large because they're tin. I mean, it's zinc that has been added to the surface in a certain way, which makes very large flakes. Sometimes when you freeze water on your windshield, you can see the crystals also with different orientations. Okay, so grain boundary is one way of increasing the elastic limit. Another one is alloys. So I didn't really speak about the alloys. I think I'm going to just make a little comment here again. What happens if you start with an alloy, like here, you add a few of these alloying elements. So you create the distortion in the system. That's one thing. What you can then do to make it even better is you heat it up. Like you heat it up to 120 or 160 degrees C. You heat it up and you keep it hot for maybe an hour or two, and then you cool it again. It's called heat treatment. When you do that, you give some mobility to the atoms. Atoms can start moving a little bit around. And what they will do is they will try to get together. So what happens is suddenly they will end up here. If they get together, they will stay together because they like them. They like to be together. They found their old friends again. Cool. It's been a long time. I don't see. And so they'll stay together. What happens is it distorts. It makes an even much bigger distortion in the web. inside the crystalline structure. And it makes it more efficient to block dislocations, and it actually increases the elastic limit even more. So we call them precipitates. A precipitate is a cluster of alloying elements. Cluster of alloying elements. They get together. One other way is cold forging. Cold forging is when you hit it and you create dislocations like crazy. If I forge something, I hit it and I hit it and I hit it, each time I'm plastically deforming it, so the dislocations start moving around, and actually you create more defects into the crystal. So you create more and more and more dislocation. At one point you have so many dislocations that they're actually blocking themselves. It's like if you add cars on streets. At the beginning you just have a few cars and everything is fine. You come 30 years later to the same city and it's a big car jam every time at rush hour. The same thing. Many dislocations will start creating some kind of an intricate net, which makes that these dislocations, which are necessary for the deformation, they're suddenly impossible to move anymore. Exactly like cars that are necessary to move fast. When you have too many, you can't move anymore. Cold forging, solid solution, that's the one that we looked at first, which is an alloying element, but it's in form of a solid solution. It means it's just dispersed. So if one atom here, one atom there, one atom there, that's already somewhat efficient. More efficient is the precipitate, and then two different things you can do. You can actually increase the number of dislocations like crazy, or you can create a grain boundary and have more grain boundaries. Those are all mechanisms to act on the free motion of dislocations. I think that's about what I wanted to say about metals. I don't think I have much more. It's an example of an alloying element, aluminum. Remember I had this slide, but it's very, very directly related to the question that came before. What they've done here is they've increased the elastic limit so much that they've actually created a fairly fragile material. And at one point you get to a stage where it's possible to break the beam. So there's you have to be a bit careful how much you increase the elastic limit, because what happens, the more you increase the elastic limit, the less you can deform your material plastically. In fact, it becomes more and more fragile. Does that make sense?
Because of all the distortions inside.
If you avoid all mechanisms of deformation, you can't deform. If I'm putting so many things into the system that it can't deform it, so my elastic limit is now very, very high, but I can't do a big plastic deformation. If I start, snaps. I have to go very high in force to start, but if I go above, it will snap. So I lose the ability of plastic deformation. So there's always a trade-off between safety, in this case, and performance. Okay, where do we find metals in sports equipment? And I would say pretty much everywhere. Arrowhead, horse riding gear, a long time ago already. And in modern equipment, everything. Shoes even have some metal spikes. All the winter sports, the size, these edges here, the metallic. On sleds, they're metallic. They're always metallic. Aluminum, discovered actually fairly recently, 1827, and again used in many applications, including pole vaulting as one of the first sports usage besides airplane and automobiles. Titanium is a metal that was also discovered in the 18th century, but started to be used more in the second half of the 20th century. Golf clubs, baseball bats, bicycle frames, and so on. Magnesium is a very light alloy and used again in similar applications. Lead, I was talking about the gloves for boxing. Gladiator would use some metal in there. Okay, ammunition, boat keel, and so on. Tungsten is an extremely heavy metal, but it's also super hard. It's much harder than stone. And if you put it on the tip of the ski poles, they don't wear out. You can make a pointy pits, and even if you hit rocks and whatever you do hiking in the summer, you will still have your very sharp ski pole tip. Okay, so much for metals. I have a few slides on polymers. Are we still okay? I know it's a bit tiring. It's is it fascinating? No, I know this is certainly, for a lot of people who haven't seen this in a long time, this is a lot of information. I realize that. And as I said, this course has been a little bit condensed. It used to be over 3 days. Now it's 4 hours. So I've taken away quite a bit of stuff. I had to leave in an understanding of fundamentals of materials. It's the title of the course. So even though I have a lot of fun examples that I can show you where metals have been outperforming other materials, where composites have been outperforming other materials, so on, I think it's necessary that we do go in a little bit into the fundamentals. I hope you don't mind too much, but I guess you're here to learn something anyway, so and not just to increase your culture of sports. So the second family of material I will talk about is polymers. Polymers, they are, as I said, backbones of carbon, very long molecules, and they're either just like a spaghetti bowl, so just randomly oriented with no covalent bond between them, or there is a few covalent bonds between the molecules, and that becomes another family, or they have a lot of bonds between themselves, like a 3D in all dimensions. They're all connected. All molecules are connected. And we call those thermosets, those thermoplastics, and then the ones a little bit in between, they're called elastomers. Everybody knows what an elastomer is? An elastic rubber band. It's a rubber. Those rubber are elastomers. The tires of a car are elastomers. So they're a bit in between those two extreme cases. And why are elastomers elastic? Well, in their unstressed state, they have this random orientation, like, they go in every which direction, but they have a few places where they're pinched, where they're solidly bonded, these covalent bonds here. Now when I stretch it, what happens is they stretch to an extent where suddenly you're starting to pull actually on the molecules. And if you take a rubber band and you pull, you will see it's easy, and suddenly you get to a limit. If you go a little bit further, you're probably it's going to break. And that's exactly what happens. You pull it, it's easy, until the molecules are stretched. Now you're pulling on the molecules. So suddenly it gets harder, and very soon after it snaps.
The elastomer is the elatomer? The elastomer is the elatomer? It's the same thing? Elatomer?
It's a misspelling.
It's probably a spelling mistake, if it's in my course. Yeah. It's on my slide. Thank you. Elastomer. Thermoplastics. So as I said, thermoplastics, they don't have any bonds between themselves, which gives them a very, very unique ability, which is all the more important today. What is that ability of thermoplastics?
Can you shoot? They can take in any shape.
You can recycle.
Yes, recyclability. You can give it a shape, like a pet ball has a certain shape, has a certain function, it has a certain life. But when you get to the end of the life of the material, you can melt it. Because if you give it enough heat, the molecules will start sliding again, like the liquid beads that I was showing when I said this is liquid metal. Well, here it will be liquid polymers. So you have it liquid in the liquid form again. And then when you freeze it, you can give it a very different shape. So for instance, a fleece jacket is made from recycled PET balls. So the recyclability is a unique feature of thermoplastics. Foams Of course, you can foam a plastic. So pretty much any plastic can be foamed. So you can use CO2, for instance, during the time when it's liquid. It foams it, and then when it's in form of a foam, you freeze it as a foam. That's how you create a foam.
Can you blow foams with helium?
Often it's done with CO2.
Yeah,
Why would you want to do it with helium? Because helium is extremely permeable. Lighter? Well, there's actually almost no weight in gas compared to material. If I was to fill all the tubes of my bike with helium instead of air, I would gain, per cubic meter, I would gain a kilogram. But my bike, in volume, has probably 5 liters. So it'd be a 200th. So it'd be 5 grams. Going through the challenge for that. The problem is helium. I mean, if you could, maybe it could work, but CO2 is actually very, very often used because what CO2 does, it dissolves in the polymer. So, like in a water of carbonated drinks, the CO2 is dissolved in it, and when you release the pressure, you foam it. Well, you do the same thing. You can dissolve a lot of CO2 under high pressures, like 200, 300 bars, a little more than your pet bottle. And you dissolve a lot of CO2 inside of the plastic. And CO2 is extremely soluble. And then when you release the pressure in one shot, it expands, and that's how you foam.
And that you can also undo, like the foaming. It's also
Well, if you can have thermal sets and thermoplastic foams. So if it's a thermoplastic foam, then you can melt it and it collapses again. And you make liquid and you can do something else from it. If it's a thermal set, you will foam it. Once it's foamed, you will create a secondary reaction, which will create covalent bond between the molecules, and then you're stuck with that chain.
So once there are covalent bonds, then it's no longer recyclable. Recyclability is no longer.
Correct. You can burn it if you want to call that recycling.
Okay.
It'll give you heat.
And metallic foams, how do you miss them?
It's a good question. So there are a few labs who have worked on metallic foams. I don't know how much you know about metallic foams. So it's not very commercially available yet.
Yeah.
But there is a lab I know of at the material science department near here, and Professor Mortensen is working on this. So what he's doing is using salt. So he's using a salt. He's infiltrating the salt with liquid aluminum. So the salt melts at 800. The aluminum melts at 600. So you can infiltrate the aluminum into the salt, and then once it's done, he is dissolving the aluminum, the salt, with water, and he's left with a foam.
Is the fact that thermoplastic are recycling by does the fact that thermoplastic doesn't have covalent bond explain why they are recycling?
Careful. Thermoplastics have covalent bond in their bone structure. What they don't have is covalent bond between different molecules.
That was my question.
That's why they're recyclable. Yes, that's why they're meltable. That's why you can reshape them and give them a very different shape. Something you have lost if you create a thermoset. The very earliest, the very earliest polymers used were at the beginning of the 20th century. Bakelite, cellulose, like the billiard balls, which helped to reduce the consumption of ivory, because billiard balls were made from ivory before that. The problem was they would sometimes explode, because cellulose is somewhat explosive. So it was not necessarily win-win for the people who were using them. But soon after they came out with other polymers to create these balls. Rubber was used for a very long time, like golf balls, hockey puck, and so on, over 100, 150 years ago. Epoxies are very much used for composites. So they are the glue to the composite. So I didn't go into too many details, but you have polyethylene, polycarbonate, polypropylene. What they are is, when I showed you the molecule at the beginning, the carbon backbone, if I rip away one atom and I put another one into place, it changes the name and it changes the property. So it's just simply a slightly different molecule.
What is PC?
Polyethylene. That's actually the most common polymer, probably highest consumption in the world. It's that rubber maybe from car tires.
Polyethylene? Is that what the one they call polyethylene?
Polyethylene. Yeah.
Polyethylene, is it?
PE. Polyethylene. Often
Yeah.
also written down as. So you have PE is polyethylene. And then you have HDPE. Sure, if you have something in plastic, you look at it, it often says what it is. Here it says PP, it's polypropylene.
What of the
PE, and then you have HDP, it's high density polyethylene, means it has longer molecules, and then you have ultra high molecular weight polyethylene. It's all the same, it just means the chain along.
the shopping bags that you get in the shop, are those polyethylene?
The what?
Shopping bags, where you go to shop and like in Coop and they give you those
Oh, the shopping bags, the plastic bags.
the plastic bags,
Trash bags, polyethylene.
polyethylene. Okay.
What about drinking water from this? Is there any particles of bottle going? No? Even after longer time?
And even if it did, you can eat plastic,
Nothing.
it come out.
Okay.
It's not heavy metals, it's not. Some plastics are biocompatible. Polyethylene is one of them. PMMA is also one of them. PMMA, polymetal metacrylic. It's plexiglass, better known under the word plexiglass. I don't have it on here. Ion ions. Okay? PC. Polycarbonate. So what polycarbonate is, as I said, all these molecules are carbon related to carbon related to carbon related to carbon with a, what is this kind of bond related? The bond here between these two carbon fibers is a neutron. No, it's a kind of a bond. Is it a metallic bond, is it an ionic bond, or a third kind of bond? Covalent bond. Thank you very much. Excellent. So we have all these covalent bonds between the carbon atoms, and then for the simplest molecule we have hydrogen. But there's one where here we have something like this. It's polycarbonate. Hydrogen and so on. And what this is a symbol. What it actually is, it's a carbon, a carbon, a carbon, a carbon, a carbon, a carbon, and a hydrogen on top. Hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here. So it's this system here. What this does, it makes it very difficult for the polymers to crystallize. They can hardly crystallize. I didn't really speak about that. Maybe I should give you a word about the crystallinity of polymers. I don't know. How interested are you in polymer crystals?
Yeah, go on, do it. Do it.
All right, quickly. So, polyethylene, that very simple molecule, can very much crystallize because the hydrogen are small, and this is very mobile. So when I freeze it, it actually will try to create as much as possible areas where it's crystalline. It's still, the molecule will still continue to have some random orientation in some locations, but then suddenly we'll find again a location where suddenly two atoms started to get close together, and another one that comes here and goes like this, and then it keeps going. So it has crystalline zones between amorphous zones. So we have amorphous, amorph means no shape. Not sure how you spell amorphous. I'm a pretty poor speller, as you probably noticed. and crystalline. Maybe with an I. Crystalline zones. So it's a so-called semi-crystalline. It's a semi-crystalline